In the previous video, we learned how to take the derivative of logarithms. In this video, we're going to use how those derivatives, as well as the property of logarithms, can help us find derivatives of more complicated functions. So first, I want to remind you of the three properties of logarithms. I have them written on the screen. If we have a log of a product, we can write that as a sum of two logs. That just comes from the fact that logarithms are exponents, and when we multiply, we add the exponents. If we have a log of a quotient, we can rewrite that as a difference of two logs. And finally, if we have a log of an exponential, we can write that as a product. We can take that exponent, bring it down, write it as a product, n times log of a. So the concept of logarithmic differentiation is when we have a complicated function, something that involves lots of products, quotients, and exponents, we can take the log of both sides, find the derivative implicitly, and because we've taken the log, we can use all those properties which allow us to turn things like products and quotients into sums and differences. And in calculus, working with sums and differences is often much easier than working with products and quotients. So I'm going to show you how this works by doing an example. I have the function f of x equals x cubed times square root of x squared plus 3 divided by 3x plus 5 to the fourth. If I want to take the derivative of this function, I would have to use the quotient rule with the product rule and the chain rule within it. So what I'm going to do, first thing I'm going to do, I think, is just change that square root into a 1/2 power. Then I'm going to take the log of both sides. So I have to take the log of the left-hand side and the right-hand side. So that f of x, I'm going to call that y, and that gives me log of y. And then I have log of my entire expression. Now on the right-hand side, I'm going to use my properties of logs to try to simplify. So we have log of a quotient, so I can rewrite that as a difference of logs. I'm going to get log of my numerator, which was x to the third, times x squared plus 3 to the 1/2, minus log of the denominator, which was 3x plus, oh, it's actually a plus 5. Let me fix that. 3x plus 5 to the fourth. Then this first term, log of the numerator, that is a log of a product. So I can rewrite that as a sum of two logs. That becomes log of x to the third plus log of x squared plus 3 to the 1/2. So I've taken this expression and I've expanded it into a sum and difference of logs. Notice that anything that was in the numerator became a positive log. Anything that was in the denominator became a negative log. Finally, I'm going to use that property that says if I have a log of something with an exponent, I can take that exponent and move it in front and write it as a product. So I've got now 3 log x plus 1/2 log x squared plus 3 minus 4 log 3x plus 5. All right, so now that we have expanded that expression, that right-hand side, as much as possible, we're ready to take the derivative. And I'm going to do this implicitly. So on the left-hand side, natural log of y has a derivative of 1 over y, and then using the chain rule, or my implicit differentiation, I get times y prime. On the right-hand side, we have 3 times ln x. The derivative would be 3 times 1 over x. Next term, plus 1/2, that constant stays there. And then natural log of x squared plus 3, that's a chain rule problem. Derivative of the outside function is the natural log. That's going to give me 1 over x squared plus 3. And then I have to multiply by the derivative of the inside. The inside is this x squared plus 3. That has a derivative of 2x. And then finally, my last term, the minus 4, the constant stays there, and I'm going to use my chain rule on log of 3x plus 5. I get 1 over 3x plus 5 times derivative of the inside, which is 3. Okay, so putting this together, we've got 1 over y prime equals 3 over x plus, next term the 2's cancel, and that's going to become x over x squared plus 3, and then minus 12 divided by 3x plus 5. Finally, to solve for y prime, we can multiply both sides by y, and then I want to rewrite my final answer in terms of x only. So I'm going to take that y and replace it with the original function. So my final answer is y prime equals x to the third times square root of x squared plus 3 divided by 3x plus 5 to the fourth, multiplied by the quantity 3 over x plus x over x squared plus 3 minus 12 over 3x plus 5. And I know this was a lot of work, but it is actually faster than trying to use that product rule, quotient rule, and chain rule, and then simplifying the derivative. Here's another example. Let's find the derivative of tangent of x raised to the x. I don't have a derivative rule for this situation because my base is a function and my exponent is a function. We only have derivative rules if our base is a constant and our exponent is a variable. That's our exponential function. Or if the base is a variable and the exponent is a constant. That's our power rule. So anytime both the base and the exponent are variables, functions of x, we're actually going to have to use logarithmic differentiation to find the derivative. So I'm going to start this problem the same way I did the previous one. I'm going to take the log of both sides, and then I have a property that says we can take that exponent. So I've got natural log of tangent of x. I'm going to take that exponent and move it in front. So x times ln tangent of x. Now I can take the derivative implicitly. The derivative of natural log of y is 1 over y times y prime. On the right-hand side, I'm going to have to use both the product rule and the chain rule. We have a product, x is being multiplied by ln tangent of x. So f is x and g is natural log of tangent of x. F prime would be 1. Now to get my g prime, this is where I'm going to have to use the chain rule. This tangent of x is inside the log, so this is a composition. Derivative of natural log of tangent of x, my outside derivative is going to be 1 over tangent x. Then I have to multiply by the derivative of the inside. The inside, tangent x, has a derivative that is secant squared. So we can put this into our product rule then. F prime times g would be 1 times natural log of tangent of x. And g prime times f, that's going to be x times 1 over tan x times secant squared. Finally, I'm going to solve for y prime by multiplying both sides by y. So I've got y equals natural log tangent of x plus, and then I took that product for the second term and just multiplied, just wrote it as one fraction, x secant squared x over tan x. And then finally, just like in the previous problem, I am going to replace that y with the original function, with that tangent x to the x. So final answer, y prime is tangent x to the x times natural log tangent x plus x secant squared over tangent x. So again, anytime you have a base and an exponent that both are variables, you're going to have to use logarithmic differentiation to find the answer. That was my last example. As always, let me know if anything is unclear.